So Olivier Michel is the head of Cyberrobotics, a company that provides the world with Webots, a fantastic robot simulator that we're also going to use in the Shanghai lectures. He has been part of the Shanghai lectures for several years now, and we are very grateful to him to supply all the students with a Webots license. And today he's going to talk about the NAO race. Olivier, I'm ready. If you want to start, the videos are
yes.
Also ready.
So can you hear me?
Yes.
Okay. And can you see my presentation?
Yes, we can see it.
Okay, great. So thank you for the nice introduction, Nathan. I'm going to present today what we are doing in terms of simulation benchmark. So at Cyberrobotics, we've been busy for several years doing competition based on our simulation software. And those competitions are actually a form of robotics benchmark that has been used by researchers across the world. And so I'm going to summarize what we've been doing so far and to introduce the new simulation benchmark we are introducing on November 1st, thanks to a collaboration with a partner, and that will be a student competition, actually. Okay, so this, as you can see, is my car, very beautiful car. And I want to introduce what are benchmarks. So my presentation may include some brand advertising. So here you see one of the most famous benchmark known in the world, which is the time a car takes to reach 100 kilometer per hour time. So if you need the best, you need to get this Porsche 918 Spider, and it will take you only 2.2 seconds to reach 100 kilometers. But this is probably not what most of the people want to know when they buy a new car. So there are other benchmarks in the car industry. This one, for example, is the fuel economy rating. That is the number of miles you can achieve per gallon. So with 1 gallon of fuel and a Toyota Prius, you could achieve 50 miles. Then this one is probably more interesting. It's more complicated as well, because it relies on a number of metrics that correspond to experiments which are done on cars. And depending on the results of the tests of the experimental benchmark, they will grant a number of stars to different models of cars. So it's called Euro NCAP 5-star security rating system, and it relies on mostly security of the occupant of the car, pedestrian, and also safety assist, which is the all the electronic that will assist the driver preventing crashes. Okay, so we do not only benchmark machines, but we do benchmark people. And here you can recognize one of the most famous human benchmark, which is the 100-meter race at the Olympics. And you can see, of course, this guy, Usain Bolt, who is the fastest man in the world. And you can see this is a screenshot from Wikipedia. You can see the ranking of the best runners of the 100-meter race in the world. And you can see some details about the benchmark condition, like they measure the wind. If the wind speed is above a given threshold, then you cannot record the performance. So everything is very precise. The distance is very precise. The wind, the type of ground, and so on. So every parameters need to be taken into account to be able to record the performance. As an example, the NAO robot would take about 100 times more than Usain Bolt to run this race. So it's not the best efficient. but my car would take 7 seconds. So my car is better than Usain Bolt. So actually we are able to build machines that are better than human at this very specific benchmark. But in robotics, we are addressing other benchmarks. As you can see, this is a game where you may recognize the German team. And this game is played by humans, but it's also played by robots. You all know this RoboCup competition where robots are playing soccer against each other. And to rank the performance is very different from a race because you don't measure a time, but you measure the performance of a team versus another team. So the official ranking is the one displayed here. It's not very relevant because you see Argentina first, Belgium second, then Germany, but you don't see Spain, for example. So it's because this ranking is computed in a very complicated way, which may not be very relevant to everybody, to what everybody thinks about ranking soccer. So other people, so this is a different kind of ranking, which is ATP ranking, which is used in tennis, also to compare the performance of players versus each other. In that case, this ranking is much more accepted by everybody. Nobody will deny that Djokovic is the first and Federer is the second and so on. So because this ranking system is different and is inspired from the chess ranking system, which is called the ELO ranking system, where when you face an opponent that is stronger than you, you may be able to win more points and to climb up in the ranking. And this one is also very well known and very acknowledged by the community. And then some people tried to make some unofficial ELO-based ranking for soccer. And the result of the ranking is quite different because you see that Spain is there, Brazil is there, so it seems to be more relevant. And Belgium is not is only 10, whereas it was very good ranking before. Okay, so in this short introduction, you could see that there is on one side absolute benchmark, like measuring the speed on a 100-meter race, or for a car or for a human. And there are relative benchmarks, like soccer, tennis, chess, where you cannot measure the performance in an absolute way, but you have to measure the performance versus another competitor. So we have exactly the same kind of benchmark in robotics. Sorry, I will go back. Yeah, we have the same kind of benchmark in robotics, like the RoboCup robot playing soccer challenge is a relative benchmark, and we also can have absolute benchmark. So now I'm going to introduce a little bit my company. So my company is developing the WebBot software for 17 years now. We have 5 employees, and we are working also closely with researchers and companies to develop robotic simulations. We have over 1,200 customers worldwide, mostly university, but also companies. And the software is used both for research and education. So, Nathan, can you start the movie? So this is a short introduction movie that presents the capabilities of the software. So, yes, I can see the movie here. So this is just, rather than giving a technical presentation on the software, I prefer to show this movie because it provides a good overview of the capability of the software we provide. So here you can see the salamander robot that was developed at EPFL. So the simulation was used to design the robot, the number of modules of the robot. It was also designed to measure the how the robot will perform in swimming. So we have included a fluid dynamic simulation in the simulator. So the robot is equipped with sensors. So here you can see the ray of the distance sensor of the robot. So the robot is using the sensor to avoid obstacles. And now it will detect that it's getting out of the water, and it will move the legs again. So those are legs turning. So this is a very different simulation based on the NAO robot. So we've been collaborating with Aldebaran Robotics to develop an accurate model of the NAO robot, which is now included with every NAO you buy. So if you buy a new NAO, you will get a license of webbots, including this simulation model, so that you can program the robot in simulation first and then transfer your program onto the real robot. So this is very appreciated for teaching, because you can have all the students working in the simulation and then have only a single robot, and then from time to time you move from the simulation to the real robot to check that the results you get on the real robot are the same. So here you can see every device is simulated, the camera, but also the touch sensors in the feet of the robot, and the distance sensor in the body, the feedback from the motors, and so on. So here again, a different simulation. We've been also working with the automotive industry, and currently we have a project together with the PSA group, so Peugeot Citroën cars. And so they are very interested in putting more robotics technology into cars. So here you can see very simple simulation of a car following the track. It's using cameras and rangefinders to detect obstacles. And here you can see webbots is not a realistic simulation. I mean, it's not simulating soft bodies, but it is limited to rigid bodies. This is why the car doesn't crash, but we're not interested to see the crash. We're interested to avoid the crash, actually. Okay. So here you can see a different simulation, which is a little bit more industry-related. It's the KUKA U-Bot mobile manipulator, which we simulated in webbots, and for which we simulated the very special wheel system. So you can see this mechanism wheel system, which allows the robot to move in any direction. Okay, this is another different simulation. Here we have this, you can see this Roomba vacuum cleaner robot. So in this simulation, we had to add some dust and to simulate the dust and to simulate the fact that the robot could clean up the dust. And here you see the simulation running in fast mode. So this is very convenient to use a simulation tool in fast mode to quickly see the results of the behavior of the robot in some environment configuration. Here you can see a modular robotic simulation where a very simple module assembled to each other and can disassemble depending on the program. So here we are exploring different locomotion system based on this modular robotic system. Okay, maybe I will not go through all the video because it's quite long and my presentation is limited, so I would like, maybe, Nathan, can you stop the video? Okay, thank you. So I will revert back to the presentation. Okay, and yeah, so in our company we have been trying to promote the software and the use of simulation by the organization of a series of competition. So we first organized the Rat's Life competition, which is basically a survival game for a robot competing with another robot in a maze. I'll show a video of that in a minute. But before that, I'd like to show this RoboCup movie. So Nathan, can you show the RoboCup movie? It's a very short movie which illustrates a competition we organized with humanoid robots fighting with each other. So you will see, okay, two robots, and the robots are trying to kick the other robot out of the ring. So it's a kind of sumotori-like game. And the robots are walking One constraint is that they have to stand, they cannot walk on all four, and they have to kick the other robot out of the ring. So that will be quite fast here. You see the blue robot is out. Okay. So we organize also a different competition like the Robot Stadium competition, which is basically a robot soccer game inspired from the real RoboCup, and the NAO race that we started recently. So here it's the Rats Live competition. So as you can see on my slide, there was a real system and a simulated system. So you could run the simulation, the benchmark in real or in simulation. So there was a feeding system. The robot had to look for food, and the food was represented by this sensor, which is on with a light and which can detect the presence of the robot. And here you can see the images taken from the real camera of the robot on the top. And on the bottom, you can see similar images taken from the simulation. So the simulation was calibrated to provide very similar images so that image processing could run the same in simulation and in the real robot. So this is all the strategy that came up from this competition. So maybe, Nathan, can you show up the Rats Live movie now? Okay. So here you can see the simulation version of the two robots in the maze. And the robots are first exploring the maze, and they are looking for those food dispensers. And as you can see, one of the robots found a food dispenser. Okay, so he got food from it, and then is going away. And the robot is getting energy from the food dispenser, but the energy is getting down as the time passes and the robot moves. So if the robots don't find enough energy, it will finally starve out and it will lose the game. So the goal of this game is to survive longer than the opponent by finding energy sources, that is those food dispensers. And possibly some strategy is to try to prevent the other from getting the food. So there are only 4 food dispensers in the maze. And so you have to remember the location of the one you found previously to be able to come back when food is available again. Because food is available, then you get it, and it's not available anymore, then you have to wait sometimes before food becomes available again at the dispenser. So you have to remember the previous location of the feeder to be able to come back there after a while. Okay, so I think we're not going to wait until the end of this game. So at the end, one of the 2 robots will die from starvation and the other will be the winner. Maybe, Nathan, you can terminate this video? Okay, thank you. So during the evolution of this competition, we could see a number of different strategies emerge. And at the end, the best strategy were the winner of the competition. So we got about 50 teams participating in that competition. And at the end, the best guys were doing complete self-localization and mapping, that is SLAM, on the environment. So they were able to recognize the feeder from image processing. They were able to explore very efficiently the maze, to recognize the landmarks in the maze, to approach the feeder, to dock, retrieve the food, but also to remember the location of previously found feeders on their internal map, and to be able to navigate very optimally to these feeders while optimizing the amount of energy they had. So it was like, we got 70 teams actually participating over the 12 months of the competition. So it was the evolution of the behavior of the robot was very interesting because it was like a genetic algorithm where at the beginning you could see very simple behavior, and those behavior went rapidly extinct because of the competition with better behavior. And for example, some of them used a random walk in the maze, but those disappeared quite rapidly because they were replaced by more efficient algorithm. And you can see here different strategies that some of them got extinct and some of them survived and some of them became dominant, like using self-localization and mapping. Okay, so that was the ranking. So every week we ran a round of competition, and the winner of a match was getting one position in the Hall of Fame. So maybe I won't get into the detail on how you could get a good ranking, but basically if you win a match against some opponent, then you would swap your position with this opponent and you would climb up in the ranking. Okay, so after this Rats Live competition, we organized a robot stadium competition where 8 robots, so 2 teams of 4 robots had to play soccer. So Nathan, can you start the robot stadium movie? So it shows a game. Actually, that was the final between Carnegie Mellon University and versus a French student. And you can see the robots in the video. They are using intensively image processing to locate the ball, to locate the opponent, to locate the goal, and then to drive the robot to navigate to the ball, to kick the ball and try to score a goal. So in this benchmark, actually very close to the real benchmark, because we were following the exact same rule as the RoboCup Standard League. So actually the Carnegie Mellon team used the same algorithm for the strategy of the robots, for the communication between robots, and for the overall decision system to drive both the simulation and the real robot. And they were competing both in the simulation league and in the real robot league. And they won actually both, the simulation and the real robot league. So that was quite interesting to see that the same algorithm could win the competition in simulation and could win the competition on the real robots as well. So maybe we can wait until they score the first goal. So if I remember well, CMU won 2-1 or something like that. And the match were 10 minutes long, I think. So I cannot very well see the score. So currently it's 0-0. I think, yes, we are very close to the goal. Is it that one? No. Okay. So as you can see, one of the very important things was to be able to recover from falling down, because the robots are falling down very often, and they have to detect using the inclinometer built in the robot that the robot is down to fire the recover behavior. And normally in the real competition, the robots are not allowed to fight each other, that is, to push each other down. In the simulation, the referee was actually not penalizing robots doing this. So this is why they were a little bit down quite often. Okay. So, yeah, I thought the goal was coming earlier, but apparently it's still a big mess with the robot. Okay. Okay, so maybe we can give up, or maybe I don't know if we're close to. Is it possible for you, Nathan, to advance a little bit in the movie? Oh yeah, that's it. So you could see at least the goal. Okay, so that was the first goal by the French opponent, and then the CMU is going to score also. Okay, maybe we can stop the movie now. I think we got it. Thank you. Okay. Okay, so now we are introducing a new competition, which is not a relative competition in the sense that there is no relative ranking of one team versus another team. It's an absolute benchmark, and it's based on the NAO robot, and it is actually a 10 meters race, and we measure the time spent by the robot to run 10 meters. So the model of the robot is very similar to the one, to the real one. That is 22 servo motors, 4 sensors, bumpers, cameras, ultrasound sensor, accelerometer, gyro, and so on. And you can drive this robot to run the 10-meter race. So, Nathan, can you start the NAO race movie now? Okay. So here you can see the NAO robot starting to run on this 10-meter race. Actually, this benchmark was deliberately made very simple so that anybody can understand what's the goal of the benchmark. It's very similar to what humans do in the Olympics. So everybody understands immediately when they see the robot, when they see the track, what is the goal, what is the performance metrics, and how to achieve that. So actually we ran this competition during summer school for 1 week with a few students, and they could improve the performance of these robots by making the robot run almost 3 times faster than it is running at the moment. So, and they spend only 3 days working on the simulation, trying to optimize the motion of the robot to get it run faster. So actually you can see the 2 viewpoints from the onboard cameras of the robot, so which is quite useful because you have to keep the robot on track, and trying to go fast, you will not go very straight and you will maybe go out of the track. So it's important to have this visual feedback to keep the robot on track. So here you see the time, and the robot will achieve a performance of 1 minute and something like 50 seconds. During the summer school, the best student achieved a performance of, I think, something like 38 seconds, which is quite a big improvement over this performance. And actually here there is a sensor in front of the finish line, which will stop the timer, and you will see the performance of the robot. So it's very simple, and we actually provide a web interface to this competition so that you don't even need to install the software on your computer to participate. You can simply log on a website and run the simulation in the cloud on a web service and see the results on your web browser. Okay. So actually, in order to design a good benchmark, and I think we have quite some experience with that, you have to address the relevance aspect. That is, your benchmark must correspond to a popular open robotics research problem. In this case, you could address this problem by a simple open loop motion and use evolutionary computation, for example, to optimize the motion. But you could also include sensors in the loop, like the gyro, the accelerometer, the camera, as I said. You could develop more complex algorithm, including this sensory loop, like the ZMP algorithm, the zero moment point, which allows the robot to have a very efficient walking. You could use also central pattern generators, which is a common technique for legged robots. The simulation provided in this competition is realistic in the sense that all what you get in simulation, there is a chance that you could transfer that into the real world. You're not doing simulation for simulation. You're doing simulation to design real things in the real world. So that's very important to rely on a simulation that is calibrated against a real device. And then it's an absolute benchmark. That is, it's valid over a long period of time. And it's very easy to compare results. You could easily say my performance is this versus the best performance is that. And the results are 100% reproducible by anybody and forever. So this is very convenient when you're trying to improve on existing things, that you could reproduce those things and you could compare with it. And so also a very relevant aspect is that a good performance results and the benchmark means progress in robotics. And in that case, if you're able to make that robot run very fast, then probably you've achieved some scientific results that are of interest for the robotics research. And then efficiency. You can have a very nice, very relevant benchmark, but you need that people use it. And in order to people use it, you have to make it very easy and simple to use. So using a simple metrics for the performance measurement, providing the tool free of charge, providing a web and a desktop version of the simulation. In that case, the programming language is Python, so it's a very simple language. We provide a sample source code also to the users so that they don't start from scratch, but they start from a working simulation. And we provide various tools like a motion editor, supervisor process, and so on. Also, I believe that in order to be successful, a benchmark has to be somehow entertaining. You have to have some fun in making the competition. And making a real-time online competition contribute to this entertaining aspect of the competition. In that case, also, we have a very nice prize for the winner of the competition, which is a trip to Hawaii Island. Okay, so here is a screenshot of the interface on the web. So on the right-hand side, you can see the simulation. On the left-hand side, you can see the simulation. On the right-hand side, you can see the Python program controlling the robot. And you can very simply modify this program, then restart the simulation, and you will see the result of your modification on the behavior of the robot. And you will see if it improves or not the performance. Okay, so basically that's it for my presentation. You could visit our website to get the direct link to the competition if you're interested to win a trip to Hawaii. And you're very welcome to participate. And I guess we'll have a question and answer session now.
Domande?
So thank you very much, Olivier, for your talk. It's great to see what you can do with DualBots, and I hope it's inspiration for our students to use the software in various ways. Maybe I might hand over to Fabio to moderate the question and answering session.
Okay, so any questions? No, I really like this NAO race, I have to say. If you can you hear me?
Yes.
Oh, okay. No, I really like this NAO race. I don't know if because it's something that we discussed already. So far, you already have some attempt. No? For sure, you had several teams competing in Benicassim at the summer school. So you already have some idea about the strategies that the teams use to try to go faster. So what was more successful so far in your view?
Okay, so in the summer school in Benicassim, the student had very little time actually to develop. They had only a couple of days to develop a better solution. So what they did is that they took the existing motion file and they tried to further optimize it to have the robot not wait at the beginning of the motion, to make each move faster. And one of the competitors did some funny thing, is at the end of the race, the robot is detecting that it's close to the finish line. The robot would, instead of walking, the robot would jump, that is fall down, to hit the sensor, and that is faster than walking actually. But you can do it only once, obviously, because otherwise you have to recover and it takes time. But he did that on the finish line, and he could save a few seconds doing this jump on the finish sensor. So that was very funny to see this solution coming out of the competition. So actually the competition will be open from November 1st, and it will end December 30th. So during the December months, you will need to be first on the ranking of the competition to earn points and to have a chance to win this first prize, which is a travel to Hawaii.
Yeah, no, you know why it's nice, because if you think to the DARPA challenge, this idea of just falling on the finish line that the student had in Benicassim is very much the same kind of trick they used by adding wheels to a humanoid robot to win the challenge. No, for people who didn't follow the DARPA humanoid challenge, but happened what the Korean team was able to win, and one of the reasons why they were able to win was that at the very, so they put some wheel on the body of a humanoid robot, so at some point they could go much faster than by just walking, and they won. So, and this idea is essential. So this may open some discussion on the competitions, right? Because is this a valid trick or not? What do you think, by the way?
No, in that case, no, because in our simulation benchmark, the hardware is fixed. That is, you have to use the NAO hardware. You cannot add some wheels or some devices to the robot. You have to write the best algorithm to control this very specific hardware. So the competition is really focused on software development, that is the control of the robot, and not hardware design. So in that case, it won't be possible, but we might imagine to set up a new simulation benchmark where the user could design the hardware, like add some wheels to the robot or whatever, sensors, or in this case, we want to really focus on the programming of the control of the robot. It's very similar actually to the RoboCup Standard Platform League, where the competitors are not allowed to modify the NAO robots, but they can only program the robots.
So the rules actually, designing the rules so it's far beyond what we want to discuss now, but it's true that the designing the rules is what makes a competition more important or not. So it changes the meaning of a competition. For instance, I think that this race is a very nice idea. No? It might be a challenge like the RoboCup one. By the year 2050, a humanoid robot will go faster than the world champion, human world champion. So now we are quite far, no? Because you may say again, no? What's on the 10 meters, the record is
38 seconds.
Yeah, so
10 meters. So we are very far away.
yeah. We have some work to do, but
sure. But in any case, the NAO robot is unable to achieve a good human performance because it's small, because the motors are limited and so on. But then, after some discussion with some people in Benicassim, we had a very nice idea to make a slightly different version of this NAO race. Instead of measuring the time spent to cover 10 meters, the idea would be to grant the robot with a limited amount of energy in joules, and to measure the distance that the robot could cover spending this amount of energy. So instead of a race, it would be more like a marathon, where you should program the robot to optimize the energy consumption while trying to optimize the distance you cover. So that is to spend the less energy to cover the most distance. And this is also very relevant for humanoid robotics research, because it is likely to yield to walking gaits that are very energy efficient and therefore very human-like and very graceful. And this is something which is missing currently in humanoid robots, and that could be also a very interesting metrics to measure on this kind of benchmark.
And it would be, last question, it would be difficult for you to allow different physical implementation to participate in the same race. For instance, the NAO against the corner ranger.
Oh no, it would be very easy. We just need to have a model of every robot, and you can put the different robot on the start line, and it's really no problem. But I mean, it's probably not fair, because if you put a robot which has stronger motors, then this robot will win not because of the algorithm, but because of the stronger motors. So we thought that for this competition, it's fair to have the same hardware so that you can fairly compare the algorithm on the different robot. But we could have a different goal and say what is the best hardware for this kind of task, and to allow different kind of robot on the start line.
No. Okay, thank you again. I don't know if there are other questions from the global lecture hall. Then we may have, okay, thank you again.